Welcome everybody to this theory and modeling theme event. I am Sushmit Sarkar. I work at the University of St. Andrews, and I'm just filling in here for my colleagues Clemens Kupke of Strathclyde University and Lilia Georgieva of Heriot-Watt, who did all the heavy lifting in arranging this session, getting all the wonderful panel together. So the theory theme in Scotland has a big history. We are spread across multiple research groups and multiple universities, and we have all done great things in the past. I come from programming languages, so I'll just say that both Haskell and ML came from Scotland. But that's just the past. We are looking to the future here, and I'm very happy to present three wonderful speakers here. We'll start with Professor Katja Komendenskia from Heriot-Watt, followed by Dr. Juliana Bowles from St. Andrews, and Nick Nacraft from IOHK. I'm sure you'll have a lot of interesting thoughts, so please send in questions. I believe there's a question button on the interface, and if you manage to work that, then I'll try to read out the questions. So I won't stand in the way of all the speakers. Katja.
Right. Good morning, everyone. It's a pleasure and honor to be invited to this panel. So I will try to share with you my perspective on AI verification and on the future of the theory theme as well. So let me check that you can see my screen. Let's take a few seconds to just make sure. So Smith, could you confirm that you could see my screen all right?
Yes, Katja, see it.
Excellent. So as you can see, my talk is called Verification of AI in Need of Programming Language Support. It actually should have been called We're Better Together. So let's see how it goes. So as you know, AI is now really becoming pervasive. I always start with the slide like this, just to put us into a very big perspective. There is autonomous cars are no longer a dream, but they're reality. They're already tested on our streets. There are smart homes, there is robotics, and there are chatbots, and you could probably suggest a few examples of your own. I've made one picture here slightly bigger than others, and this is a robot who is helping COVID-19 patient in Italy. So that's actually Italian hospital and an actual robot. If I ask you who this robot is helping, this picture is actually misleading. It feels like the robot is treating the patient. It's not the case. The robot is helping doctors. And you can imagine why, because in order to help patients, the robot has to be intelligent, all right, it is intelligent, but it also has to be trustworthy, it has to be verified. And that's the problem at the moment, because our verification technologies for AI are not quite there. They're not as advanced as our intelligent technologies for AI. With that in mind, we launched a research lab for AI and verification in March 2019. So we're just over 1 year old. And what we wanted to do from the outset is to accumulate local expertise in AI on the one hand, and there's Edinburgh Robotharium, Edinburgh Center for Robotics. So there's a clear world-leading expertise there. To combine that with long-standing history of expertise in programming languages and verification in Scotland. So these are just some pictures of members of the lab. It's constantly growing, and we always welcome members, collaborators, so please join us. But if you think of it, that's why I said that talk should be called We're Better Together. And I quite like this picture because coffee is what excites us. AI is our coffee, so AI is what excites us. But it's actually these two donuts, which is verification and programming languages, which will ultimately sustain us. So if you want to switch off after this slide, you probably can, because that's the main message. What I would like to do after this slide is to give some technical illustration to this idea. How is it that AI excites us, but programming languages and verification sustains us? And I will use just one example, Many people working in this area can give you several examples, and I will just use one, perhaps a bit more popular now, on neural net verification. So let's go straight for it, for the technical meat of the talk. Generally speaking, AI methods divide into two big groups. It's about perception. So if your intelligent system is out there, it needs to be able to see, like in computer vision, or recognize speech if it's a robot who recognizes voices. And also the reasoning task. On top of seeing something, your car should probably be planning the route as well. So it's a more symbolic method, or logical reasoning on top of understanding the speech. In today's talk, I have to limit myself to just one side of things, and I will only talk about perception tasks. So let's talk about perception in particular. So usually neural networks in all these intelligent systems take care of perception tasks. And it could be computer vision, speech recognition, pattern recognition. And these neural nets then could go into a variety of applications: autonomous cars, robots, medical applications, chatbots, mobile phone apps, and so on, you name it. So what is a neural network? Well, it's just a function, actually. It's as easy as that. It's a function from a vector of reals to a vector of reals. Well, there is a little bit of a caveat. It's a very specific kind of function. It's a function that separates inputs or data points into classes. That's how recognition goes about. So when we look in the street and we see trees, cars, and something, it's us dividing objects, recognizing objects, dividing them into classes. So let's have a look at it on a small example. You see here 4 data points. To make it easy for you to parse this information, I'll give you a little bit of a clue. It's an AND gate. It's a Boolean AND gate. So if you have a look here, there is an input x1 and input x2, and you get an output y. And you only can get 1 if both x1 and x2 are 1, and you get zeros otherwise. So easy to remember. It's the Boolean AND gate. So suppose then we wanted a neural network to learn to classify these 4 points into classes. And one class is 1 and the other class is 0, just as it should be for AND gate. Well, our easiest, simplest neuron could look like this. It's a linear function. So it's a function with 2 inputs, x1 and x2. And what I'm giving here is just a standard shape, general shape of a linear function in 2 arguments. So both arguments are multiplied by some weights, and then there's an additional bias there, what we call bias in neural networks. It's probably much better to just show you a picture of this. So these are my 4 points in 3-dimensional space. And what I want my neural network to do is to separate them like this. In particular, I just showed you linear function. So my neuron that you saw on the previous slide is a linear function. So it will look like this. And everything underneath this separating function would be my 0 class, and anything above that will be my 1 class. And then if we wanted to prettify this or put it in more conventional neural network shape, I would say, well, this neuron function actually corresponds to this neuron with 2 inputs, weights, bias, and an output. Okay. And now what you see in red are the parameters that the neural network is going to learn. So I usually initialize this neuron with just random weights, and then I pass my examples 4 points through this neuron several times, and then I optimize the weights so that the answer here is as close to my data as possible. That's how the training works. In particular, after a few iterations of training, it's possible that my neuron would arrive to these values. So 0.5 here, 0.5 here, and 0.9 there. So you could verify that that would roughly correspond to an AND gate if you start passing AND gate values. And this is actually, the idea is there. Perhaps one other important component that I should add to this picture is an activation function. So as you can see, it's just the same function as you saw before, but I'm sticking activation function on top of this old function that I introduced. And activation functions are useful. They allow for nonlinear behavior, if that's nonlinear function that I'm plugging in. Sometimes they allow for more interruptible behavior if it's a function from 0 to zeros and ones and so on. Well, people can play with them, and they're actually very often used in machine learning. And this is an example of a few more famous activation functions. Perhaps what's going to be useful for the purpose of this talk is for us to notice that they can actually be quite complex. So this one on the top is quite simple, but we have others that use exponents, sometimes logarithms, and so on. So that's an important point here, that some of the nonlinear functions used in machine learning actually can be quite sophisticated. And we can generalize now. So we've just seen an example with 2 points, with 2 input points, 1 output point in 3-dimensional space. But as you can imagine, the data could be different. And this is an example of MNIST data set, so to say, this very famous MNIST data set. It's designed in this way. So the whole data set is a few thousands of images of handwritten digits. And then when one takes this data set for training, the purpose is to make sure that the neural network that takes in this data set can recognize handwritten digits. So it's one of the classical examples in computer vision. So taking different data sets determines shapes of neural nets. You have just seen that I was fine with just 1 neuron for my AND gate, but I probably wouldn't be fine with that for MNIST data set. So for this particular data set, the minimal neural network that I'll get will look like this. So I have my input, 784 pixels, because this picture is 28 by 28 pixels. Then I have to have some decent layer here in the middle, perhaps with 128 neurons. But this is arbitrary to an extent. What's important here is that output should really be 10 neurons, because there are 10 classes for me to classify into. So that's important. So some of the bits will really be determined by the data set, so the input layer and the output layer. And there is usually some sophistication complexity here in hidden layers, but this is one of the simplest neural nets that you can imagine for the data set. Okay, so neural nets are ideal for perception tasks. They approximate functions when exact solutions are hard to get. And that's example of our MNIST data set. For AND gate, we were actually okay. We could formulate what AND gate is without neural networks. It's much harder if instead of an AND gate, your example is actually computer vision. So an exact separating function is not known, and you have incomplete data. So neural networks approximate these solutions to the best of the available data. And they are quite tolerant to noisy and incomplete data. So that's brilliant. But there are buts, as always in life. Solutions that we get are not so easily conceptualized. So we have lack of explainability, which is now quite famous. That is, the neural network optimizes weights in order to separate data as best as it can. But it's really hard to read out and say, okay, this neuron in that neural network corresponds to this concept or something like that. So that's actually quite hard to understand why the neural network got optimized in this particular way. And they're prone to a new range of safety and security problems, new compared to the standard program software. For example, adversarial attacks, data poisoning, catastrophic forgetting. This all has to do with reliance of neural networks on data, which is itself maybe incomplete, poisoned, and so on. I will not go in too much detail into data poisoning and catastrophic forgetting, but I will focus on adversarial attacks today. And it's really easy to understand what they are. Suppose I'm given an image from MNIST dataset, that's 0. And then I'm given some noise on top of it. And by the way, the first image is classified, I trained the neural network on MNIST dataset, and the first 0 is classified as 0 with high confidence. Then I add a little bit of noise, which is usually not perceptible to a human. So that's my result after I added this noise in the middle. So as you can see, if you look at these 2 images of zeros, you can say, oh yeah, maybe there's a little bit of noise, but there's not enough of noise for me to think that the second image is not a 0. However, suddenly that same neural network that was trained to optimize classification functions on the MNIST dataset suddenly says that it thinks that the second image is 5, not 0, and with very high confidence, so 92% confidence, the neural net thinks that it's a 5. So this is a classical example of an adversarial attack. The noise in the middle is the attack, and the attack was successful in that it managed to fool my trained neural network into a wrong classification. And it's, of course, a toy example for MNIST, but now imagine it's autonomous car scenario, and your autonomous car is trying to recognize pedestrians or street signs and so on. So there are plenty of scenarios when actually such adversarial attacks, whether they are of natural, come from natural sources like light or weather, or the intended attacks when they are quite dangerous in reality. So all examples of attacks usually have these features. So they're imperceptible to human eye. That's why we call it an attack. They transfer from neural network to another. And yeah, they affect any domain where neural nets are used. So even if it's natural language processing or some domains quite different from computer vision, researchers were able to craft some attacks for any domain where neural networks are used. So we do need verification. So that's the first point. Neural networks are everywhere, and this is how easy it is to craft an attack. Let's verify them. What's the problem? Let's just verify them, right? We've been verifying compilers and processors and whatnot. And we know that programs are functions from input A to output B. Neural networks are functions from vectors of real numbers to vectors of real numbers. So we should just probably roll all our technologies and verify neural nets. Let's do it. Well, neural network verification could be like any other verification task, if not for the following 4 problems. The first problem that we have already mentioned is the problem that semantics of function components is mostly opaque in neural networks. And this is different from standard software where we say, okay, so we need to verify this program. This part is about input and output. This part is about loops. This part is about something else. We could usually, if it's a program software, we could break it into logical parts. And by breaking down the problem into parts, we simplify it for ourselves and for our solvers. So this is something that we lose with neural nets. And there are other problems as well. For example, a very big number of parameters in neural nets, undecidable verification of nonlinear functions that are used in neural nets, and sometimes finding verifiable neural networks even. So when we verify standard software, we usually think that it's correct. Okay, it may have some bugs which we aim to discover, but basically it's correct. With neural networks, this assumption doesn't work. Any neural network is susceptible to some kind of attack. So you cannot assume that by taking an arbitrary neural net, you can verify it correct, because it may actually not be correct in a sense of being proven to stand against any possible attack. Okay, so let's actually try to get some sense of what these problems, how bad they are, what they actually mean for day-to-day job for a verification engineer. So normal programs, handwritten programs, have semantically meaningful parts, and we can break those into components that matter. We should cross this out for neural nets. Then what do we have instead? Only input and output of neural networks are actually semantically meaningful parts. So none of the inside parts of neural nets can be easily conceptualized or explained. Then the community came up with this idea. Right, so suppose only input and output are important. Then how about we try to verify neural nets by using this technique. It's called sometimes epsilon ball verification. So that's my image of 7 here in the middle. And that's my 7, say, from MNIST data set, the original one. And then as a verification property, what I want to say is that if I define an epsilon ball around my 7, and this is by just using some distance. Yeah, I'm saying for any distance defined on vectors, because 7 is represented as a vector of pixels. For any distance in my distance epsilon, given epsilon from my 7, I want to make sure that all those other 7s within that distance are also classified in the same class that is classified as a 7. So that is a formulation of a verification property that people go for most often. And this has to do with the fact that pretty much no other properties, natural properties, are there for us to verify. We have to reason in terms of input and output. And usually SMT solvers are used to discharge these verification conditions. So you give that property and then you ask the SMT solver to check that automatically. Actually, if we look at it as a method, we will notice that this is a kind of underneath reasoning behind it. Because the neural networks are semantically opaque, we have to do epsilon ball verification. But because we have to do epsilon ball verification, we get to the problem of overwhelming number of parameters that our solvers get as a verification task. So let's have a look at it. And I'll try to persuade you that that's actually a major problem. So we have a few thousand images in MNIST dataset, 10 classes because there are 10 digits to recognize, and each is 784 pixels. Okay, and that's our smallest network that we've seen before. So how many parameters are there? Well, first we have those 784 weights sitting here. So these are parameters that, that we pass to a solver. Then we have a layer of 128 ReLU nodes. So weights will be there. And another layer of softmax neurons. By the way, ReLU and softmax are all names of the activation functions. So overall, we have over 100,000 of parameters. And this is really for a toy example. So this is nowhere near the neural networks that are used in autonomous cars, for example, to recognize objects. So if I pass this number of verification parameters to an SMT solver, and Z3 is, for example, a leader at the moment, it just fails to terminate in any reasonable time. So we're just not there with our solvers to be able to process these kind of verification queries. So what do we do? Well, we do a few things. So some people try to reduce neural network size and then retrain. And this is an example of our recent paper, but we are not the authors of the idea. So many people do this. Or maybe reduce the neural network to a provably equivalent, or maybe sometimes use over approximation of properties in the style of abstract interpretation. So there are about a few hundreds of papers out there with different solutions to the problem. I won't actually go into details, technical details of those papers, but I want to once again trace the logic. So we start with semantic capacity of neural networks. We get to epsilon ball verification, overwhelming number of parameters. But then our way out is essentially to say, well, wait a moment, because it was semantically opaque to start with, it means I didn't really care about the neural network there at the start. So I can verify a different neural network, a smaller neural network. And here it is. So I'm cutting down the size of the network, and this network I can verify. Although it seems like a natural way to go, it's actually a very strange idea from the point of view of verification. Imagine Intel people come to me and say, verify our new processor. And I tell them, oh, I can't verify your processor. I can verify my own small processor. And would you like to sell my verification software or buy my verification software? And they'd say, no, we're actually not interested in your small processor. We're interested to verify the original. So this is an unusual idea. And this opens really a Pandora box in AI verification, because if we apply this logic now, we can do all sorts of crazy things. For example, we have a second problem in verification, undecidable verification of nonlinear functions. So the best solver on the market, Z3, can only deal with linear real arithmetic and a very small fragment of nonlinear real arithmetic, but only multiplications. So it's not nearly enough for the purposes of neural net verification, because we need exponents, logarithms, trigonometric functions. So we can't use Z3 if we have a neural net with nonlinear functions. There is a solver Metatarsky that supports all those interesting functions that we need, but only for 4 or 5 variables, but we need hundreds and thousands. So the technology is not there. Well, what's the solution? Let's linearize our functions. And I'm citing here a picture from our recent paper where we propose a flexible method of linearization of nonlinear functions. So this one is approximating nonlinear functions with a linear function on 2 points, and this is 5 points, and this is 25 points. Again, not going into much of detail with that. What I want to point out here is that we once again use this strange logic. We started with epsilon ball verification for the problem of huge parameter space. We gave a solution, reduce the number of parameters. For the problem of undecidability of nonlinear functions, we give the answer, linearize your functions. So once again, there is a repetition of this reasoning. So we had nonlinearity, but we say, well, who cares that the original network had nonlinear functions? We linearize them and then verify a linearized neural nets. And funnily enough, very similar reasoning go for the neural networks that cannot be verifiable. People say, well, if you cannot verify your neural net because it's susceptible to adversarial attack, retrain your neural network and verify the new neural network that you retrained. And there are several approaches to retraining of neural nets, adding logical constraints into loss functions, augmenting loss functions with other interesting conditions such as abstract interpretation constraints. Not going into any detail because I don't have time to go for them, just to say that once again, we see this logic. We have non-verifiable neural network, but we don't care about it. We construct another network and then retrain it and verify that one correct. So how do we close this Pandora box and get any reason out in this situation, get the way out of it? Well, the answer is, funnily enough, comes from my slogan, "We are better together." We'll need to look at this picture not as a case and as opening of a Pandora box, but as a new style of verification that is suitable for AI. And that's called continuous verification. So on the right, you have a neural network, and on the left, you have a verifier. You cannot hope to have a straight line as you do in standard verification, but you can hope to have a reasonable cycle of modifying constraints, reducing, reshaping, retraining your neural network, and perhaps repeating this several times until you get the object that you want as a verified neural network. And we see this coming again and again across several papers all around the world, researchers basically repeating this cycle. Well, why I'm saying we are better together? Because there are two crucial tasks here for logicians and for programming language experts. For logicians, solvers become increasingly important for automation. And we know that general purpose solvers are not helpful, as I hopefully explained to you. So logicians should study tractable problems and devise domain-specific solvers for neural networks. So really work on this verifier side to make it more flexible and being able to play a crucial part in this cycle. And programming language researchers have also something to do in this. It's really crucial that the whole scheme is sound, because if you get this case of retraining, changing your verification object all the time, you should ensure some invariance of some properties in this process. So we must provide sound and elegant programming language infrastructure to sustain this cycle systematically, bootstrap solvers and machine learning algorithms properly, ensure transparency, modularity, invariant, and safety checks if we want continuous verification to find its way into industrial applications. And I'm sure I'm out of my time, and I should pass microphone to Sasmit.
Thank you, Katya, for an excellent talk. I'll clap on behalf of the audience. So please send in the questions on this link on the site. There's already a question in there, which I'll read out to you. So the questioner asks, if the only semantically transparent bits are the inputs and outputs, it would stand to reason that we should be building neural networks by composing hierarchies of smaller neural networks and thus obtain transparency in the hidden layers. Would verification benefit from a composition of pre-verified components?
Neural networks themselves are known to be non-compositional. That is, actually, you saw the complex neural network. It's a composition of layers itself. So you saw a simple neural network with 3 layers. They are composed already. When people say, theoreticians say neural networks are not compositional, it means that your layer 1, layer 2, layer 3 can have certain properties, but when you compose them and then retrain, of course, because training is part of the process, the overall neural network may lose the properties that each of the layer has had. So that's a problem. So if we could verify layer by layer, that would be brilliant. An interesting, perhaps is at the moment, a little bit of hope I see is neural network community is very keen on convolutional neural nets, and the hope there is as information gets processed and gets through the layers of neural networks, the deeper layers actually have more semantic meaning than more shallow layers. And so people are trying to analyze features and weights in deeper layers, hoping to extract some semantic information from there. So that's the current kind of most interesting fresh idea that I've seen in the area. But I'm not sure about, compositional properties are a known problem for neural nets. Hello.
Okay, yeah, thanks for that. I'll give people a few minutes to think of questions, and then I'll jump in with a question of my own to give them some time. So your talk was very inspiring in showing what verificationists and programming language people have to offer this new world of neural networks, artificial intelligence. That's all great. That's a message, obviously, I like. But looking at it the other way, what does artificial intelligence have to tell us? Is there maybe new research directions that open up?
Yeah, so an active, very active direction there is you could use neural networks to tune your software and perhaps even write your software to an extent that your new software wants to repeat patterns from the previous software. So that's quite an active research area. I used to do something similar when we tried to generate new proofs from old proofs in Coq, in programming language Coq. So, but I personally despaired in this, actually, because I think mathematicians and programmers will always write better programs than AI. That's why I switched unequivocally to the problem of verification for AI rather than AI for verification. I think that's where we're needed, programming language verification experts. In this talk, I try to convey the idea that we're not just there because we just know verification and we want to help, but potentially we will be those two donuts that sustain the coffee. So I really do think that the community really needs us to help to set up
absolutely. We have
better
a lot
rules
to
of the
offer.
game.
Yeah.
Mm-hmm.
Great. Guess we should wrap up. So thanks once again for that wonderful talk.
Thank you very much. Thank you.
Next up, we have Dr. Juliana Bowles from St. Andrews. Juliana.
Hello. So let's see if this works with the sharing. Cancel that. Can you see my screen?
I can see it now. Yes.
Yeah. Okay, so can I start? Are you okay with me starting?
You're on. Take it away.
Okay. So actually, just a moment, because before I want to do something slightly different. Okay, I can start. So thank you very much for the invitation as well to give a talk about my work on this particular group within the CICSA conference. Similarly to what Katja did with, in a way, we have slightly different titles as well for what we talk about and what it should be maybe in the context of this particular conference. So I gave the talk the title as Optimizing Prescribing with SMT Solvers, because that's the work we're doing. But in the context of this, this particular conference, which is about a sustainable society, I could also have renamed it to be known as How Formal Methods Can Contribute to Improving two sustainable goals. Sustainable goal number 3, which is about good health and well-being, and the sustainable goal number 10, which is about reducing inequality. And I'll show you some of the work that we're also aiming now in direction to collaborating with people in Brazil to use some of our techniques in the context there in a way of attracting and using global research for better global health generally. So the work overall, how did it start? A few years ago, it started with a grant funded by EPSRC, where what we were aiming to do was to try to address a problem that patients with multiple chronic conditions have when they have to follow simultaneously different clinical pathways. So the idea being that they have to follow them, and there may be conflicts between them, and how could we try to use automated techniques to resolve these conflicts. This was also followed on by some projects funded by the Scottish Funding Council. So the power here was we wanted to use the power of constraint solvers, in particular already a Z3 that was mentioned before by Katja, but use them to identify the problems that we may have in clinical recommendations for patients that have complex clinical cases and typically complex comorbidities, and how we could not just find the problems, but also propose solutions that could address them. And this is some work that is still ongoing, and my postdoc at the time working for the EPSRC project is currently a Rutherford Fellow funded by MRC jointly with the School of Medicine in St Andrews, and also involved in the HDI UK Scotland work on specifically on the research initiative on precision therapeutics. So we're trying to use these techniques, so how formal methods overall can help in this context, in the healthcare context. But there's still plenty of things to do. So it's actually very interesting work still to be done in the area, more looking at it from a computer science point of view, and in particular on formal methods, but where we are doing this work with the benefit of helping medicine as well. Okay, so just a reminder of the setup. So what is the clinical context? So I mentioned people with multiple chronic conditions. So these are things that typical conditions that we all know and are familiar with: diabetes, hypertension, cardiovascular disease, arthritis, chronic kidney disease, cancer, and so on. So there's a variety of different chronic conditions out there. And unfortunately, the situation is getting worse. And actually, as population ages overall more, just in Europe alone, we can talk about over 50 million people are affected by this, by having at least 2 or 3 combinations of different chronic conditions. And globally, you can imagine this is a problem as well. What happens within the UK is that in the UK, medicine is an evidence-based discipline. So based on clinical trials, you may come up with exactly and a better understanding of how to treat individual conditions. And you have basically a good understanding for quite a lot of these chronic conditions individually. So that means you have guidelines of how to treat them, but this is always taking into account with a single disease perspective, because usually with these clinical trials, you have to focus on a disease. You can't mix things by having too many different parameters to look at. So it is natural that the understanding is very good for individual diseases. So the problem here is that if you have patients with multiple of these chronic conditions, there is a risk that following these different clinical guidelines for individual conditions, that you have problems overall. So a very common problem and a very serious problem is the adverse drug reactions that you may have from mixed treatments for multiple conditions that a patient may have. So just a bit more on statistics about this and how serious this problem is. So just alone in Europe, you may have something like unplanned admissions around 8.6 million. These unplanned admissions are not just based on drug reactions, but a good percentage of them are. And these adverse drug reactions could be preventable. So, And also they affect mostly the majority of patients over 65 years of age, and typically on what starts to be then known as polypharmacy. So when patients are on several medications at the same time, and the effects of those combinations will cause problems and will maybe require them to be hospitalized. So this was a work done, so this statistics coming out of a document that was published by the Scottish Government. There is a working group looking at polypharmacy solutions, and over every year, every 2 years or so, they kind of revise it and try to find more improved solutions. But in particular, us as computer scientists, as formal computer scientists as well, we have ways of trying to help this particular domain as well. And in particular, we could help with detecting problems in polypharmacy and detecting also inappropriate prescribing, because these adverse drug reactions are actually known. So you know that certain combinations of drugs are bad together. So you should be able to actually identify these problems. Just to scale it up, since we're talking about a sustainable society and overall globally, this is a challenging problem. The World Health Organization also initiated in 2017 a third global patient safety challenge, where the whole topic is about actually medication without harm. So trying to address and improve medication safety by strengthening the controls over medication errors and trying to avoid anything that relates to medication-related harm. And in particular, the improvements can be at all points of the trajectory where patients are required to take medication. This can be at the early stage where you prescribe the medication, to the dispensing errors that may happen, to even administering or monitoring and use, and sometimes also revising what medications patients should be on, and maybe taking some medications out. So all this is a cycle of various different stages, where mostly the work that I would consider the work we do would fit more into the prescribing, but potentially also on monitoring, and but not in other aspects, of course, which are beyond what computer science potentially could do. But one of the key areas, or 3 key areas that are identified within this WHO report, is specifically high-risk situations where patients may actually have really delicate situations, and also the polypharmacy, again, as an issue where you do need to have a better control of that and transitions of care. So this is the context of where we could fit in. And just to show you what happens within the UK, so NICE which stands for National Institute of Care and Health Excellence, which is mainly for England and Wales, actually. So SIGN is the one for Scotland, but they provide documents that show exactly, so if you Google them and you look at the website, you can see what a path treatment guideline looks like and how it gets decomposed into different aspects and different things to look at. Just in this picture here, we have a case of a patient with diabetes, type 2 diabetes, which would mean that the patient then starts following this path and potentially trying to reduce it by other ways. But if there's no other way, you might have to go into a drug treatment, and then you typically start having some options. And within one of these nodes as well, there will be more options available as well. Not in this case, but later on in combination therapies. But you can see that the trajectory means that you will get worse. Typically, the assumption as well within medicine is that the disease will progress, so you will actually eventually move on, even though we know actually that there are things to do to actually even revert diabetes as a condition. But so in this guideline, in this case, this one is the one highlighted. There's some text shown on the side. But these diagrams that are shown, these look a bit like flowcharts, but they are extremely informal, and there are some ambiguities in this as well. In particular, what happens in accordance to a diabetic expert that I talked to, what really happens is that a patient goes this way, which is the standard medication. And only if there's a problem detected will you actually deviate and try to find a different path. So it's not quite semantically what we would understand from looking at this flowchart in a computer science sense. The thing gets worse because typically a patient that has a diabetes also has other problems, and you start having to look for their blood pressure as well. So at the same time as they have diabetes, at some point you have to start monitoring that and look at potentially at some point starting introducing some medications for lowering the blood pressure. And the first line of treatment, then the second line means you add another one, plus another one, plus another one, and you already are on several ones probably from this side, plus you add other conditions, and you can imagine how quickly you might be getting far too many medications and how the risk of those interactions can start emerging as a real concern. So it is complex to try to treat these patients. There's no doubt about that. And what we're trying to propose here is just some way of helping. By no means is going to solve the problems overall. But one thing we can do as computer scientists is actually use search algorithms. So if you imagine that flowchart in a formal way, and it kind of looks like maybe a graph or maybe a tree of treatment options, what we want to do is having the forest, if you like, of different trees and different solutions that you go through, that you try to find the better algorithm, the solution for a particular patient by going through these different graphs and searching for the best combination. A combination that reduces, minimizes adverse reactions, and maybe impossible to reduce everything, but you may try to at least look for the better combination, and also what is the better drug. So if you know a particular drug is particularly suited for a condition, that's the one you should be using. And then we use efficient SMT solvers in this context. So we do it in a patient-centric way because everything becomes a constraint. You might as well add constraints to the picture which look at what the patient needs. And in this context, you can then start looking for solutions that also try to minimize the number of drugs that a patient takes. I will not go into a lot of technical details in this talk, but if you are interested in some of this, I can point you to papers, and I can also discuss with this offline at some point, since we're not that far, and virtually we can always talk these days. So anyway, there are guidelines for common conditions. These are things that are published out there. There's information on data and interactions that different drugs may have. What we did was we tried to formalize, extract the information from these guidelines in a more formal representation. And then the idea is that we feed it into a SMT solver, which in fact in our case is also a Z3. But we add a few other things. So we know about how good medications are. Maybe we care about the cost. I don't, but maybe some people do. So if they wanted that as a parameter, that would be something that you can search for as well. So you can add patient constraints as well into the picture. And then overall, the Z3 then computes and gives you with an arithmetic optimization, which I'll tell you a little bit more about in a moment. And then the idea is that you get a suggestion at the end for what should be the right combination for this particular patient. What is the goal here? And this was our initial approach. So we've evolved this approach over time as well. So the idea here is that we know about what is bad combinations across here. And we have that information. We encode that as numbers, effectively as integer scores. What is really bad becomes negative, what's really good becomes positive, and then this is about trying to find a solution that maximizes the score, right? Or minimizes cost if cost was what you cared about. So that's the approach originally, and it got evolved, but I'll show you just a little bit just to get a flavor for how Z3 would look like. So without having to go into the details of the code, but the idea is that you can declare any constant as the drugs that you're using, for example, that you have one particular stage in the treatment plan for diabetes may involve choosing between metformin and sulfonylurea, but not both. So that's what that stage is telling you. You have a function that assigns a score to a particular drug, and then you already see here that actually metformin has a better score. So when you then try to maximize the score and get a solution for this, the kind of expectation given this small subset information here would be that that's what you're going to get. You're going to get metformin as being true because that's the better one. Now, of course, you can imagine that this is a very small aspect because it only relates to one particular node in my treatment with two medications being picked, but you in fact very often have quite a lot more, and you have the overall structure, which is a lot more complex. You can also talk about conflicts, particular drugs in this case, between a drug and a disease, and between an intolerance that a patient may have. So the idea originally was just to put all that information in, give it to Z3, and give me a solution. So that was the first approach. But then over time, we've refined this and we added quite a lot of other things on the top of that. Seeing how much I can talk about this just now, just to give you a flavor for what's going on. So similarly to what we had before, we now add a few other things. We know that time matters when you give a medication matters, because if you give it at the same time, it's not the same as if you give it in the morning and you have enough time in between. Dosage also matters, or even the way a medication is given also matters. Diagnosis order also is a concern because it could mean that you might prioritize controlling a particular disease over another one. So all these different factors have to be added into here as well. Another thing is that patients very often, in terms of their preferences, they care about side effects or not having certain side effects. So it becomes then a thing about choosing a combination that works, that avoids potentially a certain side effect, and then you're looking for avoiding with a low probability of occurrence particular side effects, for example. And also from experience, we no longer produce just one solution, but we want to offer a variety of choices to the medic to choose from. And we also have in the picture a theorem prover that is actually helping us with some of the conversion into Z3. Just to add to the picture as well, we could imagine that in the context of some cases where in some countries where maybe guidelines are not clear or maybe guidelines are not actually followed, you could imagine that you would want to look at real data to actually get a better feeling for what really is happening and maybe use additional information such as biomarkers as a way of fine-tuning the whole approach. So without going into too much detail, but we started using event structures as a way of formalizing the unfoldings of what's happening in the graphs. We add any information we like on that, including priorities as well and conditions, and then we can even try to use those kind of combinations to search through for finding solutions. To give you just a very brief description of what an event structure would be, it is a true concurrent model. You have an ability of talking about parallelism, but also you have a notion of a sequence of an order of events. So you have a causality notion with over events, and you have the conflict of a choice. So in this case, this marked with the dash there. So these are two treatment options. You will for one or another, but not both. And so we have potential concurrent steps, which could be tests. We have alternatives. We have any kind of labels that we can add on top if we want to. We have priorities as well, potentially, as a way of indicating a path as a better option for that condition. And overall, the solution is then, in just a very simplified way, just to show you what we're trying to do, is if we have these models for the conditions, we're trying to search for the better path across all of these, right? Where we pick the better choice, where we look at priorities as well. So if this is the better priority, this is the path we should be picking, and we try to search for that. Then we know conflicts between medications. So some nodes may have problems because this medication with that medication is bad together. Maybe another medication, MA2 and MB2, is also problematic together. So we need to find that. Then there are a few other things that come into the picture as well. So when you look at traces for these individual conditions, you could just look at them and see straight away, okay, these two things, because they're the two drugs that are bad together, we can't have that. So we have to try to find deviations of that. But we have another thing, so we can just replace that and resolve the problem. But there's also a notion of a time, because people don't tend to get diseases all at the same time. It's typically the onset of having had something for many years that means that you introduce other things. So you really have to add that notion across time as well. So it becomes slightly kind of start becoming dephased. So we identify other problems in there. And then we can change and look for solutions that try to minimize that occurrence and then find the ideal solution. This is a very simplified description, but just to give you a flavor for what things happen, and also we can space out things a little bit more. We can also add, so we added also the side effects as another measure on top of this. And in particular, we also add the ability of talking about adding medications on top. So in this particular case, we have some conditions for treatments based on a certain variable, maybe some blood value that you have. It doesn't matter for this abstract example. We have another condition on the other treatment of disease 1. We have priority. So here it looks like actually going this path is a better option, as is going this path, but maybe that's not possible simply because of the combinations that these medications may impose, and then you might have to prioritize. So in this particular example, what we also allow for is the fact that, so if MA1 with MC2, which are these 2 points that I showed with are the kind of better ones in a way for individual conditions, have a severe conflict with one another, there is actually a possibility of adding a drug on top that will minimize the effect of that interaction. And so we could then use that. So we explored all sorts of different ways of trying to find alternatives and solutions and so on. So we can deal with that. We can also add into the picture effectiveness of drugs, the side effect likelihood, and so on, as a way of searching for things that avoid certain situations. Okay, so that's the general picture overall, and I can talk about this in detail offline if you wish. But the idea was that we use that also together with this theorem prover, and we have ability of adding information about durations, delayed starts, and so on. The nice thing about Isabelle as well is the interfaces with the SMT solver can make it easier to generate the code, but also means that we have an ability of proving things if we need to prove any properties in particular, look at the traces generated and look for some aspects of that trace. Like we could think about degrees of concurrency as an option as well within this picture. So a different angle is if we go back to medicine and talk to medics as well, we know that there is a lot of variation in medical practice, that sometimes new things appear. How do you actually change guidelines in accordance? And how do you accommodate with the reality? What do you really do in real to accommodate modern mobility? For that, you would need to look at real data, and that would change the picture a little bit. And again, without going into too much detail, but within the theme of HDR UK, which looks at precision therapeutics, they are working on tools and that point of view, looking at data, trying to improve both the drug efficacy, understanding what better drugs are out there, and also predictions for adverse drug reactions. And if we use that kind of information coming from medicine into our solution, we can also provide better prescribing over time. So in this picture here, what this would change is that we would be adding the information on the biomarkers in here coming from those studies. And we could therefore look at effectiveness already more accurately by having that information from biomarker evidence as well. And we could be looking for minimizing polypharmacy. So future things we can do. So this combination is powerful, but there is a few issues here. By using Isabelle, we are also turning, sometimes the code is not as efficient, and we may have to work on trying to improve the efficiency of the translation with the code itself. We can try to explore concurrency further and add. We actually have some recent results on this that have been published or are about to be published recently. And there's a few other things to do. In the context of sustainable society overall, there's other things that we need to look at. So as also real data that can help us look at improving our information. Also, the patient behavior itself is one key aspect. The non-adherence often is a problem, and only recommendations being followed. So there's an uncertainty here, so we could add that maybe as well to effect. And then think about other things like when you try to wean down a particular medication and introduce something else, you have to have a delay. You can't just do it from one day to the next. So can you add these elements in the tool as well to kind of predict when is the better moment to actually deviate things? So we've worked with, started showing some of the work we're doing in the context of various Brazilian hospitals, and also gave a talk a few years ago and to a young group of Brazilian GPs, which actually gave me some very interesting feedback, because what they cared about the most, which is also in line with the WHO recommendation of medication or harm, is that they wanted to just not harm. And they were concerned about potentially be doing the wrong thing. And they wanted to know, could they have a way of checking how good their solution was in the relation of the spectrum of solutions out there. So that kind of would create notions of distances and so on. And before Sasmet interrupts me, I still want to show one little video, which only takes 2 minutes. But this is about, in particular, about how to bring this solution to Brazil. This is something that we did in the context of, and I hope you can hear this.
Over a lifetime, most people experience some form of chronic disease, including mental health problems. So the combination of increased life expectancy with more and more ways to treat medical conditions often results in people following multiple treatment plans and taking more than one prescription at once. The poor, the elderly, and particularly women in these groups are vulnerable to badly managed multimorbidity. Overlapping combinations of medication and advice without full understanding or monitoring. Complex interactions that can reduce the efficiency of drugs and potentially cause adverse reaction and overdose. These outcomes increase if patients have a lower level of education. A vicious cycle of poor education, poor physical health, and poor mental health, limiting employment and life opportunities. Throw in a global pandemic and social distancing, or other social or political catalysts, and huge sections of society are dangerously exposed. It's essential we improve the primary, secondary, and tertiary healthcare provision across the country to provide a consistent service, irrespective of regional boundaries. We know technology can help us to address many of these problems and reduce issues of polypharmacy. But are there particular challenges that we're not yet aware of? We want you to work with us to develop solutions to jointly tackle the social inequality inherent in multimorbidity.
So I think that would be me. Just a few references here at the end. If there's anything you want to talk to me about offline or now, I'm happy to have any questions. Thank you.
Thanks, Juliana, for a great talk and very cool technology. And thanks also for tying it into the sustainability theme. So we have a question board which says, how do you go about modeling non-adherence? And in particular, what are the issues with validation of such models?
So I do not actually address non-adherence at the moment. It's actually extremely hard to do that. But I do believe that if one of the problems of adherence generally has to do with the fact that the medications don't work for the patient. So if the patient is experiencing side effects that they don't like, they're more likely to drop that medication, or various factors. If there is no revision of the medications, all these different things that people experience will contribute to non-adherence as well. So if you have a better way of managing and making sure that what you do is right for the particular patient, then you can probably encourage them to be more adherent. But it's not something we are doing specifically with this. It's hopefully we could have a benefit in the long run by applying these techniques, but it's not something that I was considering explicitly.
Okay. See any other questions? So I'll jump in with a question of my own. You sort of gestured in the direction of AI for healthcare and how you learn from the data. And I was just thinking of the previous talk, Katya's talk, of what are the safety things that we need to care about and how do we link these up, basically. Do you have any thoughts on that?
So specifically in this context, it was more about the fact that there will be things that the data may tell you about certain treatment or some information about the patient trajectory or a cohort of patients with similar things for which you may have information about what worked for them. And that kind of information, if you can extract constraints from there and add them to the whole approach, so that you would use that information as well as another criteria for picking what would be the rest one, as if it would influence your score for what is a good medication, then you can use that. I'm not looking at security issues in here, so I'm not addressing that aspect that Katya was talking about in terms of how the data may be incorrect. I mean, there is a risk as well of having data which is actually not giving the right picture. So we need the guidelines and the kind of experience and medical knowledge overall as a criteria as well, and balance maybe with the real data. But the context in Brazil is particularly interesting because often they not only not have they don't have guidelines that they're following particularly, but also there's different people that do different things, but they have a lack of medications actually in some cases, and they often want to plan by knowing if they don't have a supply of medication, then what do they do? And these are cases that are very, very difficult to address. But that's why, in a way, wanting to talk to them, I want to get more cases and then try to see what could a solution from an abstract point of view. So most of the time when I do my stuff, I do it in an abstract kind of computer science sense. But I try to look at the problems that come from them, abstract from them, and then see whether I can find a solution.
Great, thank you. One last question that came up is there an international body, that standardizes clinical procedures similar to UK's NICE that you talked about that might take up your approach?
So that would be interesting, but I don't think so. So usually countries have their own. What I did talk to medics, for example, in Brazil, was that they actually are aware of NICE guidelines. So they sometimes look at the NICE guidelines. I'm not aware. I'm not a medic, so I wouldn't know. But if the WHO comes with recommendations, I think they also do that for certain conditions. So I guess they would act as more standardized global recommendations. But I would still expect individual countries to do slightly different things, potentially based on their own. I mean, because sometimes also medications work differently based on the genetic of the population as well. And pathways also have the diversion. So, for example, hypertension is an interesting one. The UK has a guideline which diverges initially if depending on ethnicity. And the Brazilian counterpart of that ignores the ethnicity because it knows it actually goes straight into the path that is followed in UK for Afro-Caribbean ethnic group, because it kind of doesn't do that split. So it already knows from their local population that there is not much point in trying to consider both cases. So it has to be done slightly localized as well, I guess. But I'm not an expert in that, so I would just do what they tell me.
Understood. Well, time is marching on, so thank you again for a great talk. I'll clap on behalf of the audience.
Thank you.
So our next speaker is Nick Nefak from IOHK, and Clemens, who, like I said, did all the hard work, has just said that he can introduce the speaker. So Clemens.
Hi, thanks, and sorry for the first two speakers of today. I was bogged down with some teaching commitments, which were all related to Zoom problems. Anyway, so welcome. So I would like to welcome the last speaker and Nick Nefak, who is from IOHK. I don't know, probably a lot of you know IOHK already, but so IOHK is an organization working in blockchains, and it's one of the top 10 companies doing this with over $300 million in assets. So it's a big player in that area. And he worked with Nick worked with charities in his past, with nonprofits and NGOs. And the big kind of goal he wants is to improve the world using open financial systems. So offering open financial systems to places in the world that do not have access to financial systems so far. So I hope that, I mean, I'm sure that Nick can explain much better himself what he's doing. So I hope also that Nick is already there. So maybe if
Hi
Nick,
Clemens, thanks for the kind introduction.
Hi Nick, so just you go ahead, please. Thanks.
Okay, yeah, thank you so much. I'm going to go ahead and turn off my video just to preserve some of the bandwidth for the sake of focusing on the presentation. It's an honor to be here. Thank you for having me. And we'll go ahead and start the presentation. Okay, can everyone see this okay?
Yes, thank you.
Okay, great. So as Clemens so kindly stated, IOHK is a subsidiary of IO Global. We are a 200-member company, and I'm here to talk to you today as about one of the major aspects and the focus of our company, which is on sustainable open finance. And that means enabling a form of economic identity so that we can provide financial opportunities specifically, again, for unbanked regions in developing nations, because often those regions are forming in terms of the financial services that they can provide and the regulatory framework to support them. And it's also a unique space where we can apply blockchain and digital ledger technology to really give people access to services that they didn't have before. So we're going to tell you a little bit about who IOHK is, how and why what we're doing is sustainable. What is financial inclusion? What does that mean? Also, what are open financial systems? Why did we choose to use blockchain technology, or at least backbone that of the company, given our history? In addition to some color on why we we selected a formal methods and functional programming approach to developing a lot of these technologies, and also, if you're interested, how to get involved in the project, because it is all open source and it's possible to contribute. So who is IOHK? Well, IOHK is a company focused on building next generation blockchain digital ledger platforms. We are currently in the top 5 most traded cryptocurrencies in the world right now. So it's quite large. We're a 200-member company. Our chain is literally one of the most cutting edge next generation blockchains. And what makes it so is it uses network protocols between the nodes and the distributed architecture in a way that most people don't, to, for instance, support really fair, open, immutable and transparent transactions, and also to incentivize people in an equal way, using things like Nash equilibriums to reward the actors within the network to basically support it. So, but our fundamental mission is to be profitable, ethical, sustainable, and deliver open source software so that people can leverage it and essentially create that economic identity that we're going to talk about soon, and open the doors for themselves to have access to financial services that many of us can take for granted. So before we start, it's really important to define sustainability, because there's just so many initiatives, and there's a lot of different places in the world right now where these take different shapes and forms. The United Nations has a great starting place. They have about 17 different goals that they've developed across many different sectors and industries. And their sustainable development goals are really highlighting and overlapping with a lot of our mission statements here at IO Global and IOHK. Specifically, providing open financial services does help a great deal in terms of providing a pathway out of poverty, hunger, and good health and well-being. But specifically, providing financial services is really, and capital is a great way to begin to look at addressing system global poverty. Now, be really specific. There's extreme poverty that they've highlighted here, where people are making less than $5 a day US. And we're really focused on the step beyond extreme poverty, which is really around the emerging poor to middle class segment in places like Africa and Southeast Asia. So because extreme poverty, for instance, is many people don't even have mobile devices, and so it's difficult to even get them access to any kind of financial service or network. So I wanted to make that very clear. However, we align with a lot of those UN goals, and if you want to learn more, you can just look it up. There's a lot of really great industry initiatives, and it's worthwhile to obtain some more information if you're interested in contributing in any way to one of these segments. So what is financial inclusion? Well, 2 billion adults currently, it's even more than 1.7 billion when the census was taken, don't really have access to basic services in finance. They don't have bank accounts. Money transfers and remittance from one country to another are often very expensive for them and require a lot of overhead. Many don't even have birth certificates. Like in Ethiopia, for instance, about 38% of the population doesn't even have a national ID. So why is that important? Well, when you go to get some basic things in life, like maybe a mobile device so you can communicate with business members, friends, families, loved ones, often they'll go to the national government managed telecom, and they'll have to sit in lines during their workday, and it just creates a lot of barriers to entry. So let's talk a little bit more specifically about kind of that distinction I made earlier between kind of the extreme poor and the sort of emerging middle class in some of these countries. So I think there's a misperception specifically in Africa that there's an extreme poor population that's heavily saturated. And while that's true in some areas, the story is actually much different. Africa has the second fastest growing GDP after Asia, and at 5.5%. That's really stunning considering the overall nature of sort of the lack of financial services. But the story is that there's a really big youthful population that is now beginning to get mechanized and enabled by a lot of outside capital. However, the outside capital and lending isn't equally distributed. And so this is leading to an emerging middle class with more work opportunities. But again, those work opportunities are often funded by capital that is highly profitable for the lenders. In fact, Africa is one of the second most profitable bank lending entities in the world right now. And that's really interesting. There is also a great deal of corruption that comes along with that, and forming regulation that is presumably, but not causally linked to that correlation in terms of, driving that middle class. So soon, on an institutional level, the distribution of access to financial services really has to trickle to the average person in each of these populations. So the question becomes, how do they get included when they simply don't have simple things like an identification? In many cases, they don't have birth certificates, or even national ID cards, or even passports for that matter. So the problem becomes, how do you de-risk them for any kind of financial service when they don't even exist to begin with, as far as the national identification system is concerned? This also leads to a great deal of open possibilities for things like SIM fraud on the major telecom networks, where the mobile devices are registered without any kind of know your customer checks and currently. And so it makes it quite easy to do things like SIM swapping, which is quite popular, where folks are able to use and assume the identity of another mobile number's device and effectively use them for other purposes than intended by the primary holder. So this problem of lack of inclusion in terms of identity leads to a difficulty in obtaining access to financial services, which again makes it troublesome for the vast majority of these populations to really grow in terms of making that middle class really emerge more quickly, despite the fast growth in the GDP. So what are some of the primary drivers? We talked about them. Really, it's not that they're voluntarily excluding themselves. Some do, because again, they just don't believe maybe in the central governments, or they're distrustful or some for very simple religious reasons are not in accord. But by and large, the vast majority really are involuntarily excluded from obtaining some kind of form of identity, and therefore they can't afford the fees. They really don't have some capital sometimes, and the services aren't nearby. Even if they wanted to obtain some form of passport, it's often quite difficult through these government entities to do so. And many just simply lack a financial identity. Because they have no way of being registered within a nation, there's no way to really de-risk them. Currently, how it happens today for a lot of microlending, for those that are curious, is often there are people literally in villages who are asked to verbally vouch for people who are trying to obtain even small loans, and that has been working to some extent, but is by no means efficient in country to do any payments or lending. So it makes it quite difficult. And so where are they? Well, the vast majority here, as you can see, like 45% in these blue segments are in kind of South and Southeast Asia, parts of Europe and Central Asia as well. And the rest are really in Sub-Saharan Africa and the Middle East and North Africa. So large African segments, are involved. So again, 45% in Southeast Asia and about 34% in Africa, respectively. So let's talk a little bit about what IOHK is doing and how we can create the opportunity for identity, and what open finance is and what it means for inclusion. So effectively, it's interesting because when you look at from cradle to grave in terms of the life cycle of how identity fits and overlays with the life of a person, you really have to consider from birth many people that don't even have digital or even birth certificates. So we're approaching this to say, in a way, to say you can get a digital birth certificate issued because it's actually faster and cheaper as long as you have access to a mobile device to do that through a telecom in many cases than it is for the hospital system or healthcare service providers, or even NGOs for that matter, to issue physical cards. This happens much more quickly at a much lesser cost. So there's a very big motivation right now especially also from the World Bank perspective, because there's a very big push to try to convert a lot of these unbanked people into banking constituents. However, we'll talk about that in a minute, because a lot of that banking isn't really open or transparent in terms of how lending is occurring and where the funds go and how you can access them. So that's a big concern that creates a barrier of trust for many of the constituents based on past corruption, unfortunately, in the lending space and also in the banking segment. So really what IOHK is doing is leveraging blockchain technology, and we'll get into why blockchain in a bit, but we're going to sort of give a little allusion to, allude to why up front. And essentially the constituents need to own their data. And the more that they own their credentials, and the more that they're able to carry these credentials from one stage of their life to another, from birth into schools and universities, from schools and universities ultimately into employment, where they can make payments. And then, once they're in a self-employed state or they become business owners, then they're able to easily make payments or obtain institutional loans for those businesses, and also insure their businesses to protect their assets that they do build, and then ultimately have some way to bank openly between those entities, so that commerce can happen in a sort of direct way, business to business, without many intermediaries that are taxing them along the way with various fees, and also time to market in terms of moving the capital that they need. So this is a very interesting story. We're actually in the early stages right here. We're working with universities at the national level. We're working with some healthcare service providers as well in specific regions, namely Ethiopia and Georgia in early stages right now, to create the bedrock of these credentials so that they can be used to generate sort of profiles that are tied to that identity, which can then in turn be used to de-risk lending. And so that students can obtain the loans they need to get the training that they need, and then qualify for easier self-employment or employment with others. And as I said, if they go on to start their own companies, they can insure them and then move capital around. So it's kind of a very exciting time right now, because the technology exists, it works, and it's actually in the stages of being adopted. So let's talk a little bit more about what I mean by open financial systems, because that's sort of a very broad term, and sort of what are the details a little bit more of what that consists of. So what is open? Basically, what it means is that the interest rates and the payment fees, the legal obligations, and how the assets are distributed are transparent. In other words, they're traceable, and they can be seen as openly as when you send a parcel from one nation to another. You can see the hops that a payment, for instance, would take in the case of open payments, and who takes the fees along the way, and to reduce those hops so that it makes it a little bit faster and cheaper and better, and for these constituents to really have access to simple payment services. That does happen today with centralized systems, and we'll get into why it's different, because there's a very big mobile money saturation in Africa specifically, in adoption of that technology. However, as you'll soon see in this description, there's other hurdles there. Often the payment schedules, for instance, if you are doing any kind of open lending, are consistent, but they're not tracked, and they're not specifically tied to a set of open credentials that are owned and managed by the constituent themselves. Also, when you do end up paying off one of these microloans, it's really difficult to attach it to any profile that has any sense of metadata. So if you work between lenders, or you go from one lender to another, there's no real profile or repayment history. And this is problematic, because people who do get microloans, then how do they carry that good profile with them into a credit realm? And also, if they are able to enter some form of credit realm, how do they see their profile? Even today in the developed world, on any given day, it's really tough to know, for instance, why I have 800 points of credit versus 798, and what does that mean exactly in terms of my ability to obtain things like insurance and other downstream services, even for banking. So we're making it very transparent how to start with a simple small microlend, build upon a successful completion of that lend to enable a form of credit, to then in turn facilitate more institutional payments and even person-to-person payments at the constituent level, so that people can qualify and protect their assets, and then again through open banking have even better ways to shield and keep their money protected. So how is this better? It's a good question. By and large, what's counterintuitive about open systems is that, except for maybe people here, since they're highly technical in nature, is that it develops a consistent set of standards for profiles, and that in this way, constituents can be treated equally between disparate lenders. Even today in developed worlds, there's often a whole different set of qualifying criteria from someone who collects information for a home loan or a mortgage versus a loan for a student for education. And if we can have these standards be consistent and the profiles be consistent and the criteria be consistent, this opens up a great deal of interoperability between the lenders, and it increases a lot of lending opportunities as well to more collaboratively address the constituent market from the business perspective. So I'll be really clear with a good example. Currently today, in the payment segment, if you live in one of these developing countries, let's just say Nigeria, for instance, and you want to send $100 US from US to Nigeria, there's about 100 different ways that you can do that, and 5 that are really somewhat viable. But the problem is they don't really have a standard between them in terms of how to assess the constituent. Also, they have different ways of remitting that money. In some cases, like for Western Union, you have to go into an actual location. They do enable ways to do this for certain amounts through mobile devices. But again, often there isn't a profile that is passable between one payment entity versus another. So for some reason, you can't make it to a Western Union location, and you want to use another payment provider to remit money, maybe through some data or top-up minutes, which is very popular on prepaid networks, and send those prepaid data minutes to someone in another country, you have to use another telecom provider. And so it becomes problematic to really get any form of liquidity in terms of doing payments between different companies. And again, it opens up possibilities between companies. Another clear analogy to that is it was once impossible to send a text message between mobile network operators. That was back in 2001. I was a part of that project. We built one of the largest switches in the world to connect and carry about 98% of the traffic. And we literally connected over 2,000 mobile network operators. And in the beginning, back then, some didn't even see the value commercially of sending a text message outside of their network. That's somewhat laughable now these days, given the volume and nature of how much we text. But that just shows you how it opens up commerce on a very wide scale once there is sort of a standard in the technical standard and a business standard, so tied to a very specific capability on the constituent side. And this serves to reduce corruption. It also protects privacy. There's a lot of data breaches from these centrally managed systems, which is quite problematic these days. Even the banking entities suffer greatly at the highest levels with data breaches. And this is offset and mitigated to a large extent by having the constituents manage this in a decentralized fashion through walleting applications on their mobile device. And this also reduces a great deal of fraud when you add know your customer checks, which validate that a video that you take or a picture of yourself that you take matches even some form of identity, or in some cases we're looking at call data records and machine learning to find patterns in those call data records, so that if people don't have any identity and they've been good paying customers on a telecom, for instance, that we can help them begin to form an identity to begin with just by naturally paying their mobile phone bill. So here's an example of that. It's a good segue because this is all sort of a very ethereal concept until you look at something quite concrete like SIM registration for digital ID creation. And it kind of gives you a sense of why blockchain and ledger technology is so powerful in this instance. So Ethio Telecom is the largest national telecom in Ethiopia. They are currently in the process of privatizing their telecom infrastructure. It's publicly owned and managed by the government right now. And the big problem is that most people have to stand in lines to just obtain a prepaid mobile device and get it registered on the network. And they have to do this during work hours. And they often have to provide some form of identity, like a national ID card. So it's problematic, and it advantages people, that are in a certain segment, and they have competing telecoms now that are entering the market that will soon allow you to buy a mobile device, in a corner souk, and essentially take a picture of a SIM card to register that on your device. However, many are not taking the second step, and this is where we're starting to begin to put together some very high-level product concepts. These aren't in the market. It's not something that Ethio Telecom's currently doing, but these are concepts that are being considered to a large extent by some of these players in the commercial segment. And here's the key piece right here of all of this is, if you do have some identity, you're able to take a picture of your identity with your mobile device. And again, most of this is not smartphone capability. This is very, very possible with the existing Android device base that they have right now. And all it has to have is, obviously a camera on the mobile device, or they can, do it from the souk store itself, where they'll have a point of sale that's connected to a camera as well to enable some of these things. And effectively, they take a picture or video of themselves, and if the machine learning environment recognizes the image and they match, this creates a know your customer check, which is like bank level know your customer verification to, again, create a profile. So this is a very, very powerful step. It effectively takes what was before just sort of an anonymous device and just kind of a phone number and ties it to a very specific form of identity. And again, if you don't have a piece of identity, you can still create a credential. And some of the telecom partners are interested in using your payment history to help build some of these identities. And the national government is also really interested to do that as well, because issuing these identities is quite expensive, as is maintaining them. So it's a very concrete example of what I'm talking about. So again, why blockchain? Blockchain doesn't always make sense. It's not always the best solution, to use something that looks like a distributed database, especially if a lot of it is public, even though it is encrypted. So, why would you use that for identity specifically? Well, if you look at the rollout of current programs at the national level in some of their regions of Africa, specifically in Kenya and South Africa, sometimes their current process is really creates a lot of barriers for people because it's being centrally managed in a way that requires, like for instance in Kenya, people are having to form these massive lines to become included in their nationally managed program because they're issuing NFC cards. They're issuing just these simple cards, and you have to provide your biometrics, and you don't, that's stored in a central database, and it's actually exclusionary to a large extent because most people are just surviving each day and they can't simply get, some of these centrally managed identities. So the ability to self-serve and the ability to have that stamped quickly and reinforced by a central government entity was going to be essential. And it will also increase the amount of trust, because in South Africa, for instance, the banking entities are being used, the banks there, to deliver a lot of these NFC cards. And so for people who are unbanked, this is not only intimidating, coming from a poor segment, but it's also quite impossible to even obtain one because they don't even qualify to begin with to open a simple bank account. So in this way, it makes it a lot more tenable. So shifting gears a little bit, how did we do this? How did we develop one of the most technologically advanced and fair, open and transparent immutable chains? We did that using...
Yes. Nick, sorry, we need to have an eye on the time. So you still have about
okay.
2 minutes, I think, to.
Perfect.
Okay, perfect.
Great. We'll go ahead and wrap up. Thanks for the
okay, cool. Thanks.
Reminder. So we used a formal methods approach, which allows us to convert a lot of our theorems into actual traceable software design, which is really quite important. I won't get into the underpinnings of that, but things like Nash equilibriums, for instance, were used to do reward distribution for reinforcing the network. We are also very proud that the majority of what we do is written in Haskell, and why that's important is it makes the code a lot easier and really clear for other people to build upon. Functional programming is really, I think, a more sustainable way, if you want to talk about software sustainability, to write efficient code. And it makes it a lot easier for people to really contribute to the project, given that they know Haskell. There are other ways now that we are translating that into APIs, which I was in charge of. So you don't necessarily have to know Haskell, but the core is written in that. So that has really made things very sustainable. Also, I'd like to add, from a sustainability standpoint, our core nodes are also require 1/1,000,000th the energy of something like the Bitcoin. So from an energy consumption perspective, which I didn't mention, but I'm mentioning now, it's the Cardano blockchain, for instance, is highly efficient and can be run on something as small as like a Raspberry Pi. So how do you get involved? If you really want to help lead the charge in terms of bringing these financial services to these developing countries, we can use all the developers we can get. We already have a very sizable community. We've got over 1,000 stake pool operators that reinforce our nodes worldwide. That's one way to be a part of it. And the second way to be a part of it is to actually write code. And so we have literally hundreds of contributors contributing and writing code. So again, thanks for your time and considering sustainability and blockchain.
Okay.
Thank you very much, Nick.
Indeed. Excuse me, do you want to share? Yeah.
I don't know if you can see the questions. So I think we are a bit out of time, but I'll take at least one question. The first one that came in was, have you talked to Grameen about using IOHK technology in that context? I believe there has been some experimentation, but do you believe your technology could extend the reach of the Grameen approach?
Yeah, I have. We have, talked to many different partners in the space. Right now, it's really a question of aligning the infrastructure on the blockchain side to address more fundamental and simple problems like deployment within the network environments of educational institutions and towns. So I think we're kind of a little early to be doing some of these partnerships until we really create an easy and simple way to deploy these nodes, which we're actually doing, and also a compliant way from a privacy perspective, from an identity view. So these are like very fundamental things that are taking place in the forms of early stage phases at the national level in these countries. So once we get through those phases, then these more mature commercial sort of partnership considerations will be taken.
Okay, thank you for that. And thanks for a great talk as well. Sorry for
thank you so much.
So at this point, I would say, please, let's just continue this conversation over lunch. And there's no reason I can't say that, even if we are having lunch in different places, or maybe Nick is having some other meal of the day. Please,
it's breakfast here. Yeah, thank you.
Absolutely. So please do get in touch with any and all of our speakers and continue this discussion. And thank you all for coming. Thanks again to all our presenters. Thanks, Nick. Thanks, Katya and Juliana. I hope you have a lovely rest of the conference.
Thank you.
And thanks, Dasmeet, for excellent sharing.
You and Lilia, who's not yet here, did all the hard work. So thank you.